Hello everyone, and thanks for watching Edupedia World videos. In this session of atomic structure, we'll start with the analysis of atomic spectrum of elements. So we'll understand what do we mean by this term and how can we decipher the atomic spectrum of different elements. So basically, from what we understand, atomic spectrum is a result of the difference in energies of the orbits of an atom. Okay, so if you remember, this spectrum is nothing but arrangement of a regular arrangement of wavelengths, okay, of electromagnetic radiations. So an atomic spectrum is obviously going to be the representation of different wavelengths. But where do these wavelengths come from? Okay. What does an atom have to do with the electromagnetic radiations? Okay, so if you remember, according to the Bohr's model, the energy of an orbit, in an atom is given by minus 13.6 z square by n square electron volts. Okay, so in electron volt units, this is the energy of any particular orbit of any particular atom, where Z represents the atomic number of that atom and N is the orbit number whose energy you want to calculate. Okay. So electromagnetic radiations are a result of difference in energies of this orbit. Okay. So let's say this is your first orbit, N is equal to 1, N is equal to 2, N is equal to 3 and so on. Alright, so if you remember, whenever the electron wants to jump from a lower orbit to a higher orbit, okay, so this is 2, this is 3 and so on. So it needs to absorb energy. And how is it going to absorb energy? It is going to do so in form of electromagnetic radiation. Okay, so a photon of frequency nu and energy h nu will strike the electron, and if that photon has energy equal to the energy difference between second and first orbit, the electron can jump from first to the second orbit. Alright, so this actually results in absorption of this particular photon by the atom. Okay, which means you had lot of different electromagnetic radiations coming to this atom. Out of all those different electromagnetic radiations, this particular photon, this particular wavelength gets absorbed by the atom of the element which you have over here. So all the rest of these wavelengths which do not match any energy difference, okay, which do not match energy difference between any two orbits, are simply going to pass through. They won't be absorbed. Okay, even if they are absorbed, they are instantaneously emitted back by the atom. So in essence, they are not absorbed by the atom. Alright, so that means only the energy which corresponds to a specific energy difference between any two orbits is absorbed, and that is why you have the phenomena of absorption spectrum. Alright, so absorption spectrum is because, okay, it is because the electrons in an atom can absorb some particular photons, okay, having particular energy values, in order to change the orbit number of their electrons. Okay, so that is why we see absorption spectrum. Now likewise, when this electron, okay, now this electron has jumped from first to, let's say, second orbit, so now it is in the excited state. Okay, whenever electron is present in a higher state, okay, in a state higher than its actual original state, it is said to be in an excited state. Alright, so this electron is present in an excited state, and to make itself stable, it wants to come back to the ground state or its original state. Okay, so to do that, okay, to come back to its original state, what will it do? It will emit energy. Okay, it will release energy. And how does the electron releases energy? It releases it again in form of photons or electromagnetic radiations. Right, so how much energy will it release? It will release energy equal to the energy difference between these two orbits, the first and second orbit, which is obviously same as the energy difference which it absorbed in the previous case. Okay, so the electromagnetic radiation which will be emitted by the atom is going to be exactly same one as the electromagnetic radiation which the atom absorbed earlier. That is why we say that emission spectrum of the atoms, okay, or emission spectrum of any substance is simply the photographic negative of the absorption spectrum. Alright, so this the jumping of electron from higher orbit to lower orbit results in emission spectrum, and the jumping of electron from a lower orbit to higher orbit results in formation or phenomena of absorption spectrum, and they are both photographic negative of each other. Because you must understand how do absorption and emission spectrum are observed in an atom. Okay, so that is what we mean by atomic spectrum. Atomic spectrum is nothing but an absorption or emission spectrum of an atom. Usually we mean the emission spectrum of the atom, but it can also mean absorption spectrum. Ultimately we can use either one of them to identify the atom involved. Okay, so this particular waves, okay, which are emitted, they can be taken, their impression can be taken on a photographic plate giving us emission spectrum, and these particular waves which have not been absorbed can be taken on a photographic plate where we'll see the dark lines, and dark lines will correspond to the radiations which have been absorbed. Okay, so you already know all of this, so let's not go into further detail of that. Alright, so next thing that we need to know is that the mathematical part of absorption or emission spectrum. Okay, so for now let's just call the atomic spectrum as an emission spectrum. Alright, but we know that it can also be an absorption spectrum, which is basically just photographic negative of emission spectrum, so it is somewhat similar. So how will the emission spectrum of an atom look? Okay, so if you have an atom, okay, the atom with orbits, say it has 4 different orbits. Your particular atom has 1, 2, 3, 4 different orbits. Now electron can jump from any one of this orbit to another orbit. Okay, but it can only have so many different jumps, right? For example, what are the possible jumps over here? The electron can jump from 4 to 3rd, 4 to 2nd. Okay, it can jump from 4 to 3rd, 4 to 2nd, or it can jump from 4 to 1st. Similarly, the electron can jump from 3rd to 2nd, or it can jump from 3rd to 1st, and lastly electron can jump from 2nd to 1st. These are all the choices which it has. 1, 2, 3, 4, 5, 6. In all, the electron has 6 different choices to make here over here. Okay, this we are talking about when there are, say, 4 orbits to take into account in a particular atom. Okay, and one single electron. Alright, remember, do remember that Bohr model is applicable only for single electronic species. So this means there are only limited energy values, only 6 different energy values which are possible over here for the electron to emit. That means it can emit only 6 different kind of photons. So this means it can emit only 6 different wavelengths or 6 different frequencies of photons or electromagnetic radiation, which means here you can observe only 6 different lines being emitted in the atomic spectrum. Okay, each one of them having a particular wavelength value. Alright, so that is why we can say that the atomic spectrum of the atom is actually a line spectrum, because there are only some specific lines which are going to be emitted, and rest everywhere will be dark bands. Okay, so it will be dark colored bands, so only these particular 6 lines will be emitted. Alright, so in essence we can say atomic spectrum, okay, atomic spectrum or atomic spectra, that is plural of spectrum, are basically line spectrum. Okay, they are basically line spectrum in their nature. Alright, so do remember this, that they are always line spectrum, they are not band spectrum, and they are never continuous spectrums. They are discrete and they are line spectrums. Okay, and we know that they are emission or absorption spectrum, they can be any one of those. Alright, now lastly let's go into the mathematics of this. Okay, so see, energy value of any particular orbit is minus 13.6 z square by n square electron volt. Right, So this particular energy value when written in joules, okay, when written in SI unit, it is 2.18 into 10 to the power minus 18 joules, right? So instead of 13.6 you have this value. Okay, rest everything is same, z square by n square. Now this J represents the joules. Okay, instead of electron volts you have joules over here, the SI unit. So if the electron jumps from say orbit n1 to orbit n2, alright, or let's say it's n1 over here and n2 over here. Okay, so the electron jumps from n1 to n2. So what is the energy difference? What is the energy emitted by the electron? It is going to be final energy, that is energy of orbit n2, minus initial energy, that is energy of orbit n1. So change in energy is En2 minus En1. So what is the energy, final energy? It is minus 2.18. Okay, let's talk in terms of SI unit for now. Z square by N2 square. And what is the initial energy? It is again minus 2.18 into 10 to the power minus 18 Z square by N1 square. Alright, so minus minus over here becomes plus, and this is again a negative sign. Or what you can do is you can take the whole minus 2.18 into 10 to the power minus 18 outside. Similarly, z square is common, so you can take the z square outside. Remember, z is atomic number of the atom for who you are doing the calculations. So this is our answer. Delta E, okay, the change in energy is minus 2.18 into 10 to the power minus 18 z square into 1 by n2 square minus 1 by n1 square. Okay, so this delta E represents the energy of the photon which is going to be emitted over here. Now how do I calculate its wavelength? Okay, so it's quite simple calculation of wavelength. Once you know how to calculate energy, okay, we know that energy of a photon is basically equal to, I have put mod over here so that negative sign gets taken care of. Alright, the negative sign only indicates that the energy is being released or emitted, okay, and the positive sign indicates that the energy is being absorbed. So in this case, since energy is going to be released, you will have a negative sign in your answer. That is why I'm using mod values, because wavelengths of frequencies don't have negative values, right, obviously. So mod of delta E is going to be equal to h nu. Alright, and what is nu? Nu is the frequency, which is basically c by lambda, and c is what? C is your velocity of light in vacuum, and h is Planck's constant. Okay, so you know this, all of this formula, this we have studied before. So now you simply, for calculation of lambda, you simply reshuffle the terms. So lambda is equal to, okay, or easier way to do it is 1 by lambda is equal to mod of delta E divided by hc. Okay, so 1 by lambda becomes, mod of delta E was 2.18, okay, forgetting the negative sign since mod is there, divided by hc, and mod of 1 by n2 square minus 1 by n1 square. Okay, so this is mod. Basically you have to calculate the positive value of this. Okay, so this is what the formula for calculation of wavelength looks like. Okay, so you calculate this value, and finally you simply take the reciprocal of it to obtain the wavelength of the line being emitted. Okay, and from this calculations you can have the exact look of the atomic spectrum of any element. Okay, you can calculate all the different wavelengths which are possible, and you can construct the atomic spectrum or the line spectrum of the element. And if you remember, 1 by lambda is also called wave number. Okay, so this is basically the formula for wave number. Alright, now this value, this particular value over here, okay, let's have it in a different color. Okay, now this is an important value. Why? Because see, all of the terms over here are constant. 2.18 into 10 to the power minus 18 is constant. C is velocity of light. Okay, C is velocity of light, and this h is Planck's constant. So let's see what this whole constant will represent. So we have 1 by lambda, or wave number of any light emitted. Okay, the wave number of light emitted is given by this particular formula. Okay, where you simply take the mod value over here. So this whole term is a constant. What is the value of h? Do you remember the value of h? You do have to remember this value. Okay, so h is Planck's constant. In SI unit, it is approximately equal to 6.63 into 10 to the power minus 34 joule second. Alright, and the c is velocity of light in vacuum, which again in SI unit is approximately 3 into 10 to the power 8 meter per second. Alright, so by making this simple calculation, substituting the value of h, substituting the value of c, and using this numerator as 2.18 into 10 to the power minus 18 joule, I can get the value of this whole term, which is always going to be constant. And this whole term is referred to as a new constant called Rydberg's constant, and it is represented by a capital R and with a capital H at its subscript. Alright, so this value, when you make the calculations by substituting the value, you will see that this particular value comes out to be 1.09678 into 10 to the power 7 meter inverse. Okay, in other words, approximately you can say the value of Rydberg's constant comes out to be 1.1 into 10 to the power 7 meter inverse. Alright, so you have to remember this value as well. And see, look at the unit of the Rydberg's constant. Why is it meter inverse? This whole part, 1 by n2 square minus 1 by n1 square. Okay, so this whole part is dimensionless. Alright, so whatever is going to be the dimension of this constant, that is the Rydberg's constant, is going to be equal to the dimension of the left hand side. What is the dimension of left hand side? It is 1 by meter, that is meter inverse. Okay, so this means the dimension of Rydberg's constant is going to be meter inverse. You can also calculate it by substituting it over here. The unit of 2.18 into 10 to the power minus 18 is joule, divided by Planck's constant, whose unit is joule second, multiplied with velocity of light, whose unit is meter per second. So this unit comes out to be 1 by m, that is meter inverse. Alright, so Rydberg's constant is 1.1 into 10 to the power 7 meter inverse. Okay, so from here you can always remember, you can directly remember this formula, that wave number of any emission of light, okay, any light emitted, is going to be equal to 1.1 into 10 to the power 7 into 1 by n2 square minus 1 by n1 square. Alright, since we are taking mod value, it doesn't matter whether you are writing n1 over here or you are writing n1 over here. Alright, so this formula you have to remember. Okay, or you will have to calculate the Rydberg constant's value each time you make the calculations. Okay, so this is how we can obtain the atomic spectrum of different elements. Okay, in the next session we'll take the example of hydrogen atom in particular to go into a further analysis of atomic spectrum of element. Okay, so until next time, and once again thanks for watching Edupedia World videos.